Today we shall discuss about another method to find out the transfer function, that is signal flow graph method. Earlier we have discussed about two methods. One is by using differential equations to find the transfer function, and the other one is block diagram reduction technique. Now this is the third method, which is also used to find out the transfer function. It is also called as the graphical method. Unlike in case of block diagram reduction technique, wherein which a system is constructed using blocks, summing points, takeoff points, here in signal flow graph we have what are called as nodes and branches. A node is represented by a circle, a branch is represented by a straight line connecting between two nodes and an arrow mark indicating the signal flow direction. Signal flow direction. Here in signal flow graph there are various definitions which will be helpful for us to find out the transfer function. So in order to solve for the transfer function, or in order to determine the transfer function of the given system using signal flow graph method, we need to be familiar with these definitions. So we can illustrate this by taking a suitable example as such. So now I'm just going to draw. I'm going to draw the example. So this being an example which comprises of just nodes and branches. It's a system which is represented by nodes and branches. This being an input node, this being an output node. These are the directions of the signals which are indicated by the respective gains as G1, G2, this is G3, and this is G4. So this is how we are going to represent a given system with just nodes and branches and arrow marks. Here you can just see this is supposed to be another branch which is in between these two nodes with a gain of G5, and there is another signal which can be represented in this way with a gain of minus H3, this being H2, this being H1. So this is a given problem. With respect to this, we are going to define each term which is related to signal flow graph. The very first one is forward path. Forward path and forward path gain. So this is a term just like we had some of the set of rules in order to find out the transfer function in case of block diagram. Here also we need to follow some of the rules which will help us to find out the transfer function in case of signal flow graph technique. Forward path, it is a path from input node to output node. It is a path from input node to output node that does not cross any node more than once. That does not cross any node more than once and follows the direction of the signal flow. Meaning here you can see here this is supposed to be input node, this is supposed to be the output node. So we need to find out a path wherein which a single path wherein which there is a connection between the signal flows from input node to the output node without entering into a particular node more than once. So now you can just see here. So if I just consider this arrow mark, it's just going like this with entering into this node, then it's reaching the last node, that is the end node C. So I can consider this path. This is a path which travels from what? From the input node to the output node without entering into the intermediate nodes. These I can call it to be intermediate nodes without entering to this intermediate nodes more than once. So now I can represent these paths to be P1. Each of these paths, how many, first thing is to determine the paths. So I can have one path, this is supposed to be P1. I do represent this path to be P1, and the other path you can just see here, this is one path which is again having a connection between input node to another output node. So totally we have two paths here. So now if you want, you can just consider this, but the direction is in reverse direction, so I can't consider this to be another path. So if I just consider this, this is entering into the same particular node. This is entering into this particular node more than once, hence the rule says that no, you are not supposed to use this as a path, hence even that is not valid. So finally, I can say that for a given problem or this problem, we have only one. When gain is not given, I can just assume this to be 1. So for this particular problem, given system, there are two forward paths. This P1 and P2, they are called as forward path. Now, what is forward path gain? It is nothing but the product of the gains of this particular path. Meaning here, this is supposed to be the input node, this is supposed to be the output node. So this is a single path which is connecting from input to output, which is having G1, G2, G3, G4 as their gains. So now I can write the forward path gain for P1 path as G1, G2, G3, G4. So this is called as forward path gain. The forward path gain is defined as a product of gains in the forward path. It is the product of, so I have just multiplied each of these gains, that is G1, G2, G3, G4, and considered this to be as forward path P1 with its respective forward path gain. Now on the other hand, I have another path, that is P2 having G1, G5, and this is just multiplied by 1. So I have another path which is connecting from input node to output node without entering into a node more than once. So obviously it is G1 into G5. So this is the first case wherein which we have to find out forward path and forward path gain. Now the second definition second definition which we need to know here is loop and loop gain. Loop and loop gain. Loop and loop gain. So a loop is a path in a signal flow graph that begins and ends at the same node without entering any node more than once and following the direction of the signal. So how to identify this loop? You see here, by definition, a loop is a path. It is also considered to be a path in a signal flow graph that begins and ends at the same node. So I consider this as a particular node. You can see here it's entering into it starts and ends at the same node. So then I can consider this particular loop to be one loop which is having a gain of minus H3. Similarly, you can see here this is another loop which is starting at this node and then it is coming back to the same node. Again, this is another node, another loop. Then this is another one, that is G3 minus H2. Okay, this is another loop. Now let's consider one more. This is one thing which, but here I can consider this to be loop because the direction is in the opposite. So this cannot be a loop. So by definition, it states that a loop can be defined as the one wherein which the signal starts and ends at the same node. So I need to write down all the loops here. So I have just 3 loops here with respect to the given problem here. So I do designate these loops as L1, L2, L3. In a similar fashion for forward path gain, loop gain will be just the multiplication of the gains here. So L1 is minus H3, L2 is minus G2 H1, L3 is minus G3 H2. Pause. But a recap of the same thing whatever I have done. First one is forward path. So there are two forward paths in the given figure with having the gains G1, G2, G3, G4, and the second one being this one which connects from input node to the output node having the gains G1 and G5. There are three loops. The loop is the one which start at the same node and end at the same node. So totally there are three loops being L1, L2, L3 with the respective gains of G2 minus H1, G3 minus H2, the product of G3 minus H2 and then minus H3. There is one more definition which we need to know here, which is called as non-touching loops. Non-touching loops. So non-touching loops are defined as the loops that have no common nodes, So here we need to consider only on the loops. So this loop, that is G2 H1 being L1, this being L2 and this being L3. So by definition, non-touching loops are the loops that have no common nodes. So you can see here this L1, L3 are non-touching. They are not touching to each other. So I can just consider this to be a combination of non-touching loops because they doesn't share a common node. So L1, L3. So we have L1 and loop L1 and L3. So obviously the product of L1 and L3. So minus it will be plus. We have G2 H1 H3 being the non-touching loop gains. Here I repeat here, non-touching loops are those loops which does not share a common node. So there are totally three loops L1, L2, L3. Consider L1, L3. Obviously these two does not share a common node. They are not touching to each other. So hence I can consider this to be non-touching loop. Now I can take L3 and L2. Here if you see here, these two are sharing the same node. Hence I can't consider this to be non-touching loops. The other combination is L1, L2. These two again here, since in this particular node they are sharing a common node, I can't consider this to be non-touching loops. So there is only one combination of non-touching loops taken two at a time. So that is L1. The combination is L1, L3. This is how we have to find out non-touching loops in case of signal flow graph method. Input node. Now I just define what is an input node. So input node is a node having only outgoing branches, whereas output node is the node having only incoming. So to this particular output node, you can see here all the other signals, they are entering into this. So I can define this output node to be a node having only incoming branches. So these are all few definitions which we need to know in case of signal flow graph, just like we had some techniques which we used in block diagram reduction technique. So I repeat here, in signal flow graph we need to know about forward path gain, loop gain, non-touching loop concept. Now we have a formula which is called as Mason's gain formula. Mason's gain formula, which is named after the person who gave to find out the transfer function. So Mason gain formula is used to find the overall transfer function C of S by R of S. So we all know the definition of the transfer function. A transfer function is defined as the ratio of Laplace transform of output to the Laplace transform of input when all its initial condition is set to 0. So here using Mason's gain formula, we need to find out the transfer function, which is the ratio of C of S by R of S, using what? Signal flow graph method. One of the advantages of this method is here we are not altering the graph. If you can recall block diagram reduction, we finally when we arrived with the transfer function, the blocks were rearranged using the techniques which we used in the block diagram, whereas in case of signal flow graph, we are not altering the whole of the system, we are finding out the transfer function. So mathematically, this that is transfer function, which is again denoted as T of S, which is the ratio of C of S by R of S, is defined as summation for all values of K, Pk delta K by delta. This is the formula which is given by Mason to find out the transfer function using signal flow graph. I repeat, so transfer function is given by C of S by R of S, that is the ratio of output to the ratio of input, which is equal to summation for all values of K, Pk delta K, whole thing upon delta. Let's see what this Pk, delta K and delta represents each here. Pk represents here the gain of the kth forward path between R of S and C of S. It is the gain of the kth forward path between R of S and C of S. So here Pk represents the forward path. So in our problem here we have two forward paths, that is P1 and P2. So obviously respectively we have G1, G2, G3, G4 as the gain to the forward path P1, and G1 and G5 for forward path 2. So here summation K, so this K becomes 2 here because we have two forward paths here. So obviously we have two paths here. So Pk is gain of the kth forward path between R of S and C of S. Now delta, this delta is given by a formula. Delta is given by the formula 1 minus summation of loop gains. 1 minus summation of loop gains plus summation of non-touching loops loop gains taken 2 at a time. This is 1 minus summation of loops plus summation of non-touching loops taken 2 at a time. In alternate sign changes we need to know. First it is minus, then it is plus, now again it is a minus. Summation of non-touching loop gains taken 3 at a time. Meaning here I have just considered 2 here. There may be a chance wherein which one more loop you have like this. So there can be 3 loop combination wherein which they are not touching to each other, meaning they are not sharing a common node. So like this we have to find out taking 3 loops at a time, taking 4 loops at a time, depending upon the number of loops present in the respective problem. So like this it goes on alternate. It's an algebraic summation, that is alternate plus minus, after minus it becomes plus summation of non-touching loop gains taken here 3, now it becomes 4 at a time, and so on and so forth. This is how we have to find out the delta which is in the denominator. Now let's find out what is delta K. Delta K depends upon delta k depends on the number of forward paths. So suppose if we have 2 forward paths, here we will be having correspondingly 2 delta k's. So how do we define this delta k is, delta k is obtained by delta, that is delta k is defined as delta minus summation of loop gain terms in delta that touch the kth forward path, that touch the kth forward paths. In other words, we can define this delta k is obtained from delta by removing the loops that touch the kth forward path. So same as delta, but we need to find out, we need to take the loops that touch the kth forward path. Those loops which are not touching to each other, we need to discard. This is how the delta k is found out. So this is the Mason's gain formula, which will help us in order to find out the transfer function using signal flow graph method, or the formula given by Mason. That we shall consider an example in order to illustrate the same to find out the transfer function. Here is a problem to find the transfer function using Mason's gain formula in another way. Given a problem as such with nodes, branches, loops, now we have to find out. The first and the foremost thing is to write down the formula, that is Mason's gain formula. T of S is given by the ratio of output, Laplace transform of output to Laplace transform of output, that is C of S by R of S, which is given by summation for all values of k, pk delta k upon delta. This is supposed to be the Mason's gain formula in order to find out the transfer function. Given as an example, this is the Mason's gain formula which will help us to find out the transfer function C of S by R of S. Given as this example, we need to find out all the that is, first is the forward path. So we need to find out how many paths are there in this formula. So as we all know, a forward path is defined as a path from input node to output node without entering into a node more than once and following the direction of the signal. You see here, this is the one which signifies a path number 1. So I do call it as path number 1, P1, with the gains G1, G2, G3, G4, G5. So I am going to write the path gains to be the product of each of the gains in the respective path, that is G4, G5. This is how we find out the number of paths. We need to find out all the possibility of the paths which connect from input node to the output path. So next, let's see whether we have another path or not. Obviously this cannot be the forward path because the direction of the arrow is in the opposite, so I can't consider this to be a path here. Now you consider this, even this cannot be, so there is only one path in this, with path being P1, which is G1, G2, G3, G4 and G5. Next is to find out the number of loops here. So now a loop, by definition, it is a path which starts at the same node and ends at the same node, following the direction of the signal. So if I consider this arrow mark, you can see here it's starting and it's ending. So I can call this to be one loop with L1. L1 being this one and L2 being another one. This is supposed to be another one which starts and ends at the same point. So this is supposed to be L2. And here also there is one loop which is starting and ending at the same. So I can consider L3. We need to find out whether another loop, whether a loop is existing or not. You can see here, this is the another loop. It is starting and it is ending at the same, starting at the same loop and ending at the same loop. I can treat this to be L4. Any other loops you have, you can find out, but I could see here only 4 loops with respective gains here. So totally we have 4 loops as L1, L2, L3, L4 with loop gains being minus G2 H1 and L2 being minus G4 H2, L3 being minus G7 H3 and L4 being G2, G3, G4, G5, G6, G7, G8. So G2, G3, G4, G5, G6, G7, G8. So this is how we have to find out paths loops here. Now is to find out non-touching loops combination. So since we have 4 loops here, I need to find out the non-touching loops combination here. So let's take first two loops, that is non-touching loops taken 2 at a time. So I consider first L1 and L2. Obviously these two are not touching to each other, so I can call this, I can consider this to be non-touching loops. So loop 1 and loop 2 are non-touching to each other. So obviously their loop gains is G2, G4, H1, H2. So here also minus, here also the product will be plus. So the loop gains here of this combination of 2 loops taken at a time which are not touching to each other is G2, G4, H1 and H2. Now let's see another combination. L1 and L3 are not touching to each other. So I can consider even this loop. So loop 1 and loop 3 are not touching to each other, so I can consider these two to be the combination. So this is G2, G7, H1, H3. Next L2 and L3, loop L2 and loop L3 are not touching to each other. So G4, G7, H2, H. This is the product of the gains of the loops loop 2 and loop 3. Any other loop combination? Now I can take this loop because this is L4 is also one of the loop. But if you see here for L4, L1 is touching, L2 is touching, L3 is touching. So I can't consider the combination of L4 to any of these 3 loops. Hence that combination is not existing here. So I now define this non-touching loops as non-touching loops that does not share a common node. So here you consider these 2 loops, they doesn't have a common node. This combination they doesn't have, and obviously this combination they doesn't have any loop which isn't common. Now it does not stop at here. It is a combination, non-touching loop combination, 2 loops at a time. But according to our delta, it continues with non-touching loops taken 3, 4 and so on. We need to see whether any combination of loops which are non-touching to each other taken 3 loops at a time. So obviously here I take this L1, L2, L3. You see here this is a one combination of loops which are not touching to each other, meaning they are not sharing a common node. Hence I have one combination of non-touching loops taken 3 loops at a time. So that will be loop 1, 2 and 3. So the product of all these will be minus G2, G4, G7, H1, H2, H3. This is how we determine the combination of non-touching. Now I've taken 4 at a time. So if I consider L4 here, obviously this is a loop wherein which the all other 3 loops are touching to each other. So hence the rule does not satisfy. Hence I don't have any combination of loops taken 3 at a time. So I have only one combination of non-touching loops taken 3 loops at a time. Finally, we have to find out delta here. So delta by definition, it is 1 minus summation of loops. So we have 4 loops, L1 plus L2 plus L3 plus L4. Then we have plus summation of non-touching loops taken 2 at a time. So we have 3 combinations such as L1, L2 plus L1, L3 plus L2, L3 combination. Next it is minus summation of non-touching loops taken 3 loops at a time. So I have one combination, that is L1 plus L2 plus L3 plus any other combination of non-touching loops taken 4 loops at a time. There is nothing. So hence I end up with this. This is nothing but the whole of the delta here. So I have just find out forward paths here, loops here, non-touching loop combination here, delta, but what is remaining is delta k here, in order to substitute in this formula of Mason's gain, given by Mason's gain, so that we have to find out the given transfer function. Now as I told here, delta k is found out by, it depends on P1. Suppose if I have one path, so I can have, will be having delta 1. So if we have 2 paths, will be having delta 1, delta 2 and so on. So delta k depends upon the number of paths here. I need to find out delta k. So by definition, delta k is found out by same as delta, but you need to consider those loops which does not touch that particular forward path. Meaning here P1 is this particular, P1 is this, that is forward path is G1, G2, G3, G4 and G5. So the loops are L1, L2, L3, L4. If I consider L1, this is touching this forward path. If I consider this L2, it is also touching this part. If I consider L4, it is also touching, but I find here L3 to be not touching to this. So I need to consider only L3 but not the other loops. So now